And oh, you know what? No, I'll tell you a little bit more about the printouts in a minute. So we've handed back the Scantron printouts. Just a reminder, there's SI today at 2:30 over in Teaching Academy. And we have another exam coming up. So getting to SI, even one time a week is quite helpful. Wednesday, 3 o'clock, we're good. So that's good. All right, now homework 6. I said I would get it ready for you by Friday morning, but I got diverted. I have this huge exam for my big Monday, Wednesday, Friday class, and just got bogged down in that. But it's squared away now, and it's a good practice. It's 4 problems, starting with a basic kinetic energy calculation. And matter of fact, you can see it here with the apple. And then doing a couple more fancy ones. There's a couple good formulas in the little table there at the top. And I've set it to be due on Friday at midnight, 11:59 p.m. Friday night. So instead of having all weekend to work on it, you have all week to work on it. Okay, from today until then. And I may, hopefully you guys get a lot of good attempts on it. And I would suggest, as I have before, that if you get stumped like on homework 6, post a question in discussions. I love hearing from you in messaging, and many of you message me with questions about this or that. However, if it's about homework, it's better if you post the very same message, whatever you would ask to me, post it in discussion. Start a new thread or add it to somebody else's thread if it's the same problem or same topic. And that way, everybody in here will be able to read up on your question and how I reply and how your classmates reply. And so far, the classmates have been doing pretty good with replying and stuff, so that helps out. All right, now about your printouts, a couple things I want to point out to you. You can see your errors on these. Now, about the printout itself, there's a little percentage value in the upper right, I guess. That's not the percentage of your test because the Scantron doesn't know anything about the other 3 points and then the 3 bonus points. So ignore the percentage, but do realize that the raw score is the same as your Scantron score. So that part is good. But it doesn't go up to 50. It only goes up to what, 47, right? Okay, and then don't forget the other 3 points and then 3 bonus points on top of that came through clickers, and all that stuff is already in web courses. If you look up your errors, you can see, well, like I got number 17 wrong. And then if you go to the blurb file, which I've posted, there's a new page. It's linked to the home page. It's the exam blurbs page. And it has a little PDF with a little description of each question. It's not verbatim, but it is kind of the gist of each question, except for the matching. Those don't get blurbs. But for the true, false, and the multiple choice, yeah. Also, if you take that blurb file, it's a PDF, and then print it out, and then use it with your Scantron printout, you have a nice little mini study guide for the final. So like if number 17 is, you got number 17 wrong, okay? And you look up number 17 on the blurb file, and the blurb file looks a little bit like this. You look up number 17 and it might say Newton's second law, basic calculation. All right, and so that tells you, okay, for the final, I better make sure I get a little extra studying on that particular topic. Okay, now I'll do this for the other the other 2 midterms. And so you have between your midterms, your Scantron printouts, and the blurb files, you have a nice little mini study guide that's really accentuates or um, points out the areas where you need a little extra study. All right. Another thing I want to point out, it's not on the notes here. I want you everybody look very carefully at your printout right now, and I want you to see if there's any question that has two answers. All right. It'll say A comma D or something like that. And it'll stick out because everybody's supposed to have one dot or one letter. Okay, anybody with doubles? Nobody has doubles? Look very carefully. All right, now so that means everybody's good for doubles. But the other thing, it's possible, and what happens with doubles is you bubble in, option B, and then you change your mind, erase it, and bubble in, option E or something like that. But then what happens is if you don't erase well enough with the first one and you leave the other one bubbled in, the machine sometimes reads that as two dots and marks you wrong. Okay, so now if you have a double, we can check it against your actual Scantron because the human eye will be able to tell if you erased it or not. Okay. Another thing to look on there. Look at your. We're not done with the Scantron printout. Take a look at it carefully. If you have something that says blank, all right, that will be marked incorrect as well. All right, and we can go and see if you have just a really faint dot bubbled in, or if you have uh, a real blank. You've just forgot it. Anybody have any blanks? Okay. All right. Good. So those of you guys with blanks, bring your Scantrons up to me. Oh no, your name's already on it. So bring them up to me at the end of class, and I'll go root around in the big pile of Scantrons and see if I can figure it out. Okay. You may have a blank, in which case, there's no change to your grade. But if you have a dot that's true and is just really faint and didn't get picked up by the computer, then I can give you a point for that. Kelsey. No, I'm not going to publish the test itself in the blurb file, but the blurb file is enough to give you kind of a flavor of each problem, and it may be enough to help you remember the actual wording of the problem. Although it's been over, I was supposed to do this last Tuesday and couldn't do it. But the exception to that, Kelsey, is if you come to office hours, as some students have already done, you can look up you can look at the actual test. And the ground rules are in office hours, you can look at the test. You may make notes on each question that you like, but you may not copy verbatim. All right. So that way you can actually look at the test results or the text of the test. So office hours for that. All right. Any other questions about the exam Scantrons? Okay, let's keep going. No, because I don't have office hours. Our office hours are Wednesday from 11 to noon. So yeah, it's possible, if you send me a message in web courses and we'll maybe work something out. All right, now just to remind you, exam 2 is coming up on March 5th, and guess what? If that's the Tuesday before spring break, all right. Now I want you to listen carefully. As Arnold Schwarzenegger, the Terminator, says, listen, he holds up his hand, his bare metal hand, and he says, now listen to me very carefully. If you do well as a class on exam 2, and if we are still ahead of schedule as we are today, then I might just give you the Thursday off after the test, which is the Thursday directly before spring break. Is there anybody that's against that? Raise your hand. Were you going to raise your hand? No. You're in favor of it? You're in favor of? Okay. So if you're in favor of that, raise your hand. Day off on Thursday before spring break. Oh, I don't see everybody raising their hand. Okay. That's not raising your hand. That's better. Okay. I saw somebody up here. It's like this. Anyways, okay. Anyways, I'll try. Hopefully we can do that. A strategically placed exam. All right. So we got that to look forward to. So let's work our you know what off and get ready for exam 2. And if we can crush it and we're still ahead of schedule, ding, no class Thursday before spring break. All right. Let's get back to work on energy as a dynamical concept. And have your clickers out because we're going to do some clicking here in a minute. And what we're going to do, you know what we're going to do? We're just going to go through an example. And then you're going to work out an example on your iClicker. All right? So, as I frequently do, I use a frozen chicken as an example. So, let's say that this frozen chicken has a mass of 2.6 kilograms. It's a monster. And it's moving to the right. Right? So it's got a little bit of speed. And you know, the thing about kinetic energy is if you're moving west at at 12 meters per second or east at 12 meters per second, you have the same kinetic energy. You don't have the same momentum, but you do have the same kinetic energy. So kinetic energy doesn't have a spatial direction. It's just a number. Right? And there's something profound about that in the theory of relativity, but be that as it may, let's do an example together. A frozen chicken, 2.6 kilograms, it's a monster. Moving rightward at 12 meters per second. All right. I just dreamed up a couple numbers, you know, just for, you know, not too bodacious, but not, you know, 1 and 2 and stuff like that. So there's a little bit of topography in our data. All right, so here's our formula for kinetic energy. And you know what we're going to do? Just write it down. Ke equals 1/2 mv squared. And that's the result of a big old calculus formula that Sir Isaac Newton didn't even calculate kinetic energies. He worked with momenta, though, but not kinetic energy. So let's do our plug-in. Plug in the stuff that we know. And the stuff that we know is 0.5 for the 1/2, 2.6 kilograms for the mass m, and then 12 meters per second, and it's quantity squared. So 12 meters per second inside the parentheses, and then square the parentheses. All right, so that's your first step, your plug-in step. And hey, you guys, if you have a calculator, you can just go to town right now, if you know what you're doing. And just, you know, you're going to need your calculator out, so get it going. And we're going to use calculators on the next iClicker question. Okay. All right, here we go. So now what I do, you know, when I'm showing you step by step, and I know some of you get a little nervous about the math, you know, and try not to get too far behind and stuff. The next move, I like to put together the 0.5 and the mass and just simplify it a little bit. So those first two terms, hold on a second. This is the hotline to Stark Industries. Hold on a second. Stark Industries. Tony Stark, Iron Man. Oh, good. Hold on a sec. My arc reactors. All right. Let me put this back in my pocket. It's still kind of bulky. They're trying to make it smaller, but okay. So that's my first move. And if you're doing it pencil and paper, that would be a good second move, actually. And then pencil and paper, take the 12 and square it, and that's 144. And then take meter per second and square it. So that's meter squared per second squared. And it's inside, both of those are inside the parentheses. All right. So now we're doing good. And all you got to do now is multiply 1.3 times 144, and you get 187.2. And then for your units, you have kilogram meter squared per second squared. And hey, you guys, that's a joule. So you could write down just a capital J for joule. So that's good. Or, you know, sometimes I like to leave it as kilogram meter squared per second squared. It's perfectly fine. And I might want to use it later and have to cancel some stuff. And, you know, that's good. All right. Questions about this? I don't want to leave anybody behind on this. And I know some of you, this is pretty cinchy, but there's a bunch that might want to review something here. So raise your hand if you have a question. Yeah, fire ahead. Well, all we're doing in this, is it because we're not doing a stopping distance that we're not using VF minus VI? The answer to that is we're not doing a stopping distance problem. We're just doing a calculation of a kinetic energy, which you do in the middle of or as part of stopping distance or stopping time problems if you want. Okay, and we're going to do some more of those. All right, and there's some stopping distance and stopping time problems on homework 6, and there probably will be on homework 7 as well. So you'll be. Yeah, so if you're trying to put together usually the work formula is what you want to use for a stopping distance problem. So if you have a stopping distance problem, usually you're going to have to calculate at least one kinetic energy, just like this, okay, from the given information. So number one here, the frozen chicken given information is 2.6 kilograms rightward, and then number two is also given information, the speed of 12. So now, if I wanted to figure out, if I had a friction force and I wanted to figure out, how long does it take to stop, then, then I have more stuff to calculate. But just for this example, we're just doing kinetic energy. All right, just so everybody has a good example of kinetic energy, a basic calculation. Another question. Okay, let's keep going. Now, the next one that we're going to do is 8.4 meters per second. And we're going to do an iClicker question. So get your iClickers fired up. You see, oh, I better turn mine back on here. Now, let me ask you a question. And you know, you're going to calculate the kinetic energy, but let me ask you a common, hopefully this is a common sense question. Um, has the object sped up or slowed down? Slowed down, okay. So it was at 12, now it's at 8.4. Question number 2, does it have more or less or the same kinetic energy? It's going to be less. It's going to have the same, 2.6 kilograms, but the V squared part is going to be smaller. All right, so let's figure that out. Oh my goodness. I got to pause the podcast or the YouTube for a second. My slides are slightly out of order. Hold on. Okay, go ahead and calculate the kinetic energy for the final speed, 8.4 meters per second. And you know what? I've got to do the same thing on my. And then type in your number to the nearest tenth of a joule. Okay, just like this one, the example is to the nearest tenth of a joule. So type in your answer, and let me figure it out myself so I can grade it. Can't believe it, I forgot that slide. Yeah. Round to the nearest tenth of a joule, just like this one. Okay, that one was 187.2, and I think this one will give you something point something. You're supposed to be on DD. Hold the power button down till it flashes, and then type DD. Got it? Did you get Go Nitro? All right. All right, so 8.4. Okay. Let's check to see what you guys have got. All right, you guys are doing pretty good. Oh, I see 2 people that rounded to the nearest hundredth of a joule. Give me the nearest tenth of a joule, please. Good. One more needs to do that. Okay, 1 minute. 40 seconds. 30 seconds. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 0. Okay. And raise your hand if you typed in 91.7. Okay, great. And yeah, you just do it the same. The only thing that's different is that the second parenthesis right here in the third equation block, this is a different number. Okay, it's I don't know, 70 point something. All right. So there you have it. Now let me do this and let's keep going. Now I want to talk about energy levels in Earth's gravitational field. And the way that we're going to work out this concept of gravitational energy, it's the simplest energy for us to work on. We're actually going to work out some more basic stuff using iClicker for a basketball of mass 0.62 kilograms. Ooh, that should be kilograms there. Okay, so the mass of the basketball, and we're going to look at it. I've got the sketch over there to the side. Straight down free fall from rest at 0, and then we're going to calculate it after 18 meters of drop. Okay, so it's going to be really going by the time it has fallen 18 meters. So here's what we're going to do. First of all, we're going to calculate the weight force. Okay, because work is force times delta x, or in this case, force times delta y. So we have a vertical weight force, and it's falling, so we have a vertical delta, we have a delta y, all right? So we're going to calculate the work through a drop of 18 meters. So delta y for us is going to be minus 18 meters. And then we're going to figure out the corresponding change in the kinetic energy. And you know how we're going to do that? We're going to do it by calculating force times delta y. And then we're going to think it over. All right. Now, first question. Hit your refresh key, please. And let me switch over to alpha to multiple choice. Next question is multiple choice. Here it is. What is the weight force of a 0.620 kilogram basketball? Go ahead and calculate that real quick. What's the formula for the weight force? What times what? Mass times G. Okay, 30 seconds. If you have your calculator, this should take about 2 seconds to do. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Yeah, most of you guys got this one right. 6.076 newtons downward. Now, in the calculation, you want to use that as, when you're calculating with this, instead of the word downward, you'll replace it with negative 6.076 newtons. All right, when you get to it. All right, now, next question. For a falling basketball, is delta y parallel or anti-parallel? Anti-parallel means opposite direction. Parallel means exactly the same direction. And notice here that I have the weight force written in capital W equals negative 6.076 newtons, and I've got a downward arrow. So when you're doing these energy calculations, the minus signs, for instance, for the weight force are pretty important. So you have to pay careful attention. All right, 30 seconds. It depends. Cannot be the answer. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, the correct answer here is A, parallel. They're in the same direction. The delta y is negative, downward, it's dropping, and the force is in the same direction. So what that means is the speed is increasing on the way down because the force is in the same direction as the motion. So it's helping you get faster and faster. And that means your kinetic energy is getting bigger and bigger as you go down from 1 meter down, negative 1 meter to negative 2 meters, going down to negative 18 meters. All right, next question. Which formula should you use to compute the work? So the energy levels in Earth's gravitational field, we're starting by the effect of gravity on its kinetic energy. So that's kind of that's our hook. That's where we get in on the energy levels. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, we're doing good. Mg delta y. And hey, you guys, as you write down in your notes mg delta y, make a note that g is negative in this equation. So when we trade in a nut, when we do our plugins, that would be a negative 9.8. And also delta y is a negative. All right. And you're dropping negative 18, so your delta y is negative 18 meters. So what that means is in this formula, you're multiplying negative times negative, and that means you've got a positive. That means the change in the kinetic energy from 0 at the top to some positive number down below, the change is positive. It's speeding up. Anything that has a positive change in the kinetic energy, we say that the field does positive work. Let me repeat that. The gravitational field does positive work on this basketball because the force and the displacement, delta y, are parallel. It speeds up. If the basketball were on the way up, then you'd have displacement delta y positive going up, and the weight force is still down. So now you have opposite directions. You have a positive delta y, and you still have a negative 6.076 newtons. So your kinetic energy change is going to be negatory, all right? Or the work, you would say the work is going to be negatory. Okay, so this is actually calculating work. All right, now, let me close this window. Hit the refresh key. Now we're going to calculate it. All right, we're going to calculate the work done. And let me change and you're going to type in a number. Okay, to the nearest tenth of a Newton meter, nearest tenth of a joule for this basketball. And you've already got the specs for it. The mass is 0.62, the weight force, negative 6.076 newtons. And now you just got to calculate mg delta y. Hey, wait a minute. Is delta y positive or negative here? Negative. Okay, so. And we'll do, and for those of you that are a little unsure, let me, okay, now hit your refresh key again and do the answer over again. Sorry. Make sure the sign is correct. Make sure you round off correctly. It's gaining speed, so the force should be a positive number. Or excuse me, it's gaining speed, so the work should be a positive. And this is what you're calculating. You're calculating the work, F delta Y. Okay, 1 minute. You guys are doing pretty good. 30 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, good. Raise your hand if you had 109.4. Very nice. Okay, good. Now, for those of you that didn't, and I know there's a few, let's just go through the steps. All right, so your first plug-in step is right here, and we already had mg figured out. So that's negative 6.076. And as I mentioned before, you have to keep the directionality negative signs intact. All right. And then the drop distance is 18 meters, so that's a negative 18 meters for delta y. And they multiply out to 109.368, and then in this round off system here, 109.4. All right. Now, let me pause for questions. Yes. Yeah, this is the work. This is the work formula. F times delta X or F times delta Y. So whatever force you have, the force could be you pushing a grocery cart, or it could be gravity like here. So if you're pushing a grocery cart, you've got delta X horizontal. But if it's free fall or something, delta Y, up or down. So, but it's basically called the work. Question: Is it the work or the? The question was, is it the work or the workforce? And the answer is, it is the work. Workforce is not a physics term. That's an economics term. Okay. Another question. Yes. Uh, that's the same. A Newton meter is the same as a joule. The question was, how come it's not joules instead of nm? And my answer is always, a Newton meter is that's perfectly fine. If I was giving a written exam, which I do for my other lecture, my Monday, Wednesday, Friday class, so that's why they get swamped with work. But a written exam, if you wrote down Newton meters instead of joules, still be correct. Okay. If you wrote down kilogram meter squared per second squared, Deanna, it would be ding, that would still be correct. All right. So they're interchangeable. It's just, sometimes, one is nicer to use than the other. Now, let's do some thinking. Let's keep going. All right. Let me ask you this. Here's question 4. We're thinking it over. We have a change in kinetic energy from 0 at rest at y equals 0 elevation, where you drop the basketball, down to minus 18 meters. So there's a gain of kinetic energy. Is it possible to figure out the speed at that elevation? Yes, no, or maybe? What do you think? Could you do it? Raise your hand if you think you could. If you think you could do it. Dan, you think you could do it? Anybody else? Okay, good. You think you could do it? What is your name again? Ryan Clark Collins. Okay. Uh, so there's a challenge for you. If you if you move from point A to point B and you gain a certain amount of energy, or for that matter, if you lose a certain amount of energy, kinetic energy, can you calculate the speed? And these guys think the answer is yes, and it is. Because if you know the new kinetic energy, 109.4, that's equal to 1/2 mv squared at that elevation. And you know what the m is. So the 1/2 m is still, in this case, it would be 0.31 kilograms. So you have 109.4 joules. No, Deanna, what you'd have is 109.4 kilogram meter squared per second squared equals 0.31 kilograms times v squared. So if you divide both sides by 0.31, you get v squared, and then you can square root that and you can get v. So it is possible. Now, 4b, the basketball gains kinetic energy, so that's nice. Is there something else that loses energy? That's our question. Go ahead and write that down. That's a rhetorical question that introduces us to this very next idea. The thing that loses joules or Newton meters or kilogram meters squared per second squared is something called potential energy. The potential energy, the gravitational potential energy of Earth. So when a baseball rises, it loses kinetic energy. And if we define gravitational potential energy, GPE, as minus F delta X, or in this case, minus F delta Y. So the work we just did was F delta Y. If we now define potential energy as minus F delta Y, then that means that at point 0, at Y equals 0, we've got 109.4 joules of potential energy. All right? So here's your formula. Gravitational potential energy, or the change, actually this should be the change in the gravitational potential energy, minus mg delta y. And the minus sign out in front is opposite of. The G also still contains negative 9.8. The delta y would be negative if it's falling, but it would be positive if it's going up. So if something's going up, you have a positive delta y, you have negative 9.8 for G, and you have that minus sign out in front of everything. So if something's going up, you're gaining gravitational potential energy. You're losing kinetic. So the reason that this is nice is because we can then model ballistic trajectories, or just a straight up pop up, as an exchange of energies. All right. And so just as in collisions with momenta, we can think of exchange momenta, exchange forces and exchange momenta, delta P for the exchange of momenta, plus or minus delta P. Same thing here. We're going to exchange energies. All right. So for every joule of kinetic energy lost on the way up, which is what happens, that goes into a joule of potential energy for the system of Earth and basketball. Kelsey. Repeat. You put in the minus sign in front of the, so F delta X or F delta Y's work, right? So, and that means change of kinetic energy. If you define potential energy as a minus sign in front of the work, so minus F delta X or minus F delta Y, then you can style it as something that's exchanged as you move. Potential energy is exchanged to kinetic energy and back and forth as something goes up and then it comes down. All right, so that's why we're doing it. All right, vice versa, a joule of potential energy lost on the way down increases kinetic energy by 1 joule because it's falling. All right. So this idea of potential energy, it's kind of abstract, but it allows us to think of exchange of energies. And one more thing is true. The total energy, capital E equals kinetic energy plus potential energy, that is a constant. The kinetic energy changes, and so does the potential energy. But if one of them goes up by a joule, the other one goes down by a joule, so their sum doesn't change. The sum is the total mechanical energy. Right? So here's the formula, and this is the formula for, this is what we call conservation of total mechanical energy. The sum of the kinetic and the gravitational potential energy is a constant. Question? Yeah, if it's going up, minus F delta Y is a positive number. Okay? And we interpret that as meaning that the potential energy of the system, the Earth and basketball system, uh, is increasing, joule by joule as you go up. Okay. And at the same time, as you go up, your kinetic energy is decreasing joule by joule because you're slowing down. A pop-up slows down eventually. But then it comes back down. And so now your delta Y is negatory, your work is positive, and the change of potential energy is negative. You're losing potential energy. So at the top of the arc at apogee, you have maximum potential energy, minimum kinetic energy. And at the bottom, just before impact, you have maximum kinetic and minimum potential energy. And the sum of the two always adds up to the same number of joules. And we're going to show that right now. So what I want you to do is draw a little kind of a table like this. All right. And we're going to calculate the energy levels of a 2-liter bottle of Mountain Dew. And up at elevation 10 meters, and we're going to hold it. All right. So from the floor, 0 meters down at the bottom of the picture, up to the top, your delta Y is positive 10 meters. All right. And so you lift it up 10 meters and then you hold it. Okay. So at that point, it doesn't have any kinetic energy, but it has potential energy. So you go minus 2 kilograms times minus 9.8 times positive 10 meters. Right. So let's figure out what that change is. So the GPE of a 2 kilogram or a 2-liter bottle, that's 2 kilograms, going 10 meters up, it's positive. Let's figure out that number now. All right, so that's your next clicker question. And hit the refresh key because this is a multiple choice. All right. What is the GPE? 2 kilogram bottle of Mountain Dew, 10 meters up. It's 0 at Y equals 0. But at 10 meters up, it's a big positive number. So you're going minus m times g, negative 9.8 meters per second squared, times positive 10 meters. And you guys are doing pretty good here. I see a lot of correct answers. "30 seconds, starting now." "15 seconds. You guys are doing good. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah. Ding. Most of you got it. Very good. The correct answer is 196. All right. So now you can go back to your table and write in 196 for the gravitational potential energy up there. Now, what that means is the total mechanical energy, capital E, is also 196. You can now calculate GPE and kinetic energy at any level that you want. So if I tell you, all right, calculate GPE at elevation 7 meters, you can do that, just like you did for 10. And then whatever number that is, it has to add up with the kinetic energy to 196. So for instance, down here, just before impact at y equals 0, the kinetic energy is everything. It's now completely converted to kinetic just before impact. All right, so 196 for kinetic and zip zap for potential energy. And those two numbers, these are the two numbers that exchange. So as you go up, the kinetic energy gets smaller and the potential energy gets bigger by the same amount. So the kinetic energy gets smaller by a joule, potential energy gets bigger by a joule. They just trade joules. All right, so the kinetic and the potential add up to the total, 196. All right, now, here's a table that you could make. And notice, you guys, that I've totally filled in the total mechanical energy column. Once you get it, you just put ditto marks all the way down in that column. Now you can't put ditto marks in the, get my cursor over there. Come on, baby. You can't put ditto marks in the GPE column. You can't put ditto marks in the KE column. But you can put ditto marks all the way down here, right? Now, here's the strategy. Go ahead and write this down. The first step is always calculate GPE. All right? And, you get whatever you get. Then subtract that from total, and that'll be your kinetic. The difference between potential and total is kinetic. Because it's either potential or kinetic. And they always add up to the same number, but they might, So here's another way to think about it. Halfway between 10, so at 5 meters, you've got 50% kinetic energy and 50% potential energy. So let's see, that would be, what's 109 point, what was it, 109.4? For the, no, it's 196. So at five, go ahead and write in 5 meters if you can on your table. 5 meters elevation, you got 98 and 98. 50-50 split. Because you've dropped half your altitude. So you no longer have 196 potential, you have 98 potential. Therefore, you also have 98 kinetic. And once you get the kinetic energy column, then you can mess around with 1/2 mv squared and figure out what the speed is. That's a brain burner. So I might put a brain burner on your homework 7 tonight. All right. You'll definitely have some practice with this table concept. So you'll have some tables, and I might put a brain burner speed calculation on there. So here's the homework lookout. Homework 6 due Friday at 11:59, plenty of time. But homework 7 will be due on Thursday at the normal time. Okay, you're dismissed. Oh, you guys with blanks, don't forget to turn them in up here. Hey. Oh, okay. Just give it to me. I'll put it over in the blank. Is that a blank? Okay, good. Ooh. Register it? Okay, do you have to dash off to class right now? Okay, hang out and let me get these papers out to these guys. And if we have a little bit of time, I can get you. All right. So let me turn on the lights. Blanks? Okay, this is good. That's all you have to do. I'll give this back to you on Thursday. Any blanks? Did you have a blank? No? Okay. All right. Have you got a test? Right. Okay. I'll get out of here real quick.